Hello everyone. So how are you doing? Let's start slowly. I need to rush through things. I'm gonna wait a few minutes for everybody to come. But yeah. Let's see. Check. Hi Simon. How's it going since last week? Nice. I've actually finished this earlier than. I mean, I put the slides online yesterday, but I finished them earlier. But I kind of forgot to do that because I to put them online and to announce the class because I was too busy playing Unicorn Overload these days. Quite good. If you get the chance, it's. I tend to like Vanillaware games, but this one's pretty nice too. Has some programming even. Yeah. Okay. So this one's gonna be a bit lighter than the class last week, though. So that's a good thing. Yeah, and of course, next week we're gonna have our first class on game design specifically, and then I'm going on a holiday for a bit. Therefore, it's let's see, we're gonna have a bit of a gap, but yeah, it's gonna be nice. Let's see how much time. Yeah, I'm gonna start in a minute. Yeah. Then I'm gonna rush through the class just to go back to playing Unicorn. No, just kidding. I'm doing it more. I'm doing it properly. Yeah. I've got the timer on hand. Okay, then let's get started. This. So, hello everyone. So today we're gonna welcome to the first, to the no, to the not to the first, to the third, the third session of the game dev class. So, first time we're talking about art this time. So, if you remember, last week we saw how to program and how to design a prototype, and today we're gonna talk about the visual part of games, more specifically the both 2D and 3D graphics, but not in movement, just the static parts. So, because of course, like it's only a fraction of it, but I think this is a better separation than 2D and 3D because we're still because the same concepts apply in both. So today we're gonna see about a few words about general art direction, and a few tips with that, and as well as some but mostly we're gonna talk about some of the more technical side and how it also links with the other parts of games, because of course this is an artistic domain, so it's not as easy to give straight answers. Like it's not programming where I can give you say, yeah, the math is like that, it's always good. No, it's something you also have to feel out for yourself, and that's not also my main domain. Also considering this was made for people in computer science first and foremost, as a class, people that were in this not masters but at university for computer science. It does have that that focus at times. But yeah, I hope you'll still enjoy that. But yeah, and the next time we're talking about that, we're gonna talk about how to animate, how to use VFX, all of that. But here today is just this part. But let's start with the questions. Like if you remember do you remember last week's class correctly? So let me get the poll up. Okay. So, what node structure can we use to make a platformer character in Godot? So, do we start with a sprite that has a kinematic body and a collision shape as children? Do we take a sprite that has a kinematic body as a child that itself has a collision shape as a child? Do we take a kinematic body and give it a collision shape and a sprite as children? Or do we take a spatial node, or a node 2D node, depending on if you do 3D or 3D, and give it a kinematic body, collision shape, and sprite as children? What do you think is the correct answer here? giving it a few. As usual, it's not about being always correct. It's also about seeing if you make a mistake. It's not an exam. But yeah, see, so 3. I think you're alone, Simon. So it was indeed that. You do want a kinematic body as a root, because you want the physics body as the root, because that's what is going to move, and the rest has to be attached to it. The collision shape must be a child of the kinematic body in order to be attached to it. Therefore, it always goes here. And the sprite is a child of the kinematic body, so that it can move with the rest. And that way, you can also adjust the sprite position and the collider separately, which is very useful. Okay, I got a second one to be done. So how do we add acceleration to an entity? So once again, so is it position? We add the acceleration to the position. We add the acceleration times delta time to the position, or do we add the acceleration to the speed, or the acceleration times the delta time to the speed, in order to have the acceleration, to add the acceleration to said entity. Oops, I forgot to translate speed. Okay, and so speed plus equals acceleration times delta time, you said. And that's also correct. We can check it once again with dimensional analysis like we did the last time. Speed is in meters per second, and acceleration is in meters per second squared. So we have to multiply by seconds in order to get meters per second, and that means our formula is correct. Is not necessarily semantically, but at least it's not wrong. That's what it tells us. So yeah, good job. So then, let's start with. So I'm gonna talk about 2D first, then 3D. But yeah, let's start with 2D and general things, including the art style and the artistic direction. So the thing is that so the art style is part of said artistic direction. The artistic direction is the global way you talk about the visual language of the game. What it's gonna look like, what does it convey, all of that, that's part of the artistic direction. So it's responsible for the coherence and global style of your game, which is a bit hard sometimes to really visualize, but it's one of the most important things. Even if your graphics are not as good, having a good artistic direction is going to do a lot more than any kind of technical skill itself. So what you want to, when you make one, so I'm not going to be able to teach exactly how to make a complete art direction. That's a whole other, not only with just a class, but a whole job, whole university course, university years. So that you want to keep in mind like the feelings you want to evoke in the player, with that world, all of that. You want to keep your technical limitation in mind. Like you can't do anything you want depending on if you're aiming for mobile or another platform, or even current day platforms. It limits really quickly, actually, depending on how you go at it. And you also have your production limitations. You can't just make you have to make all of those assets. So therefore the time you have to spend to that or to optimize it, all of that, that's also stuff you have to keep in mind when you do your artistic direction for your game. That's as always, a holistic view is often necessary for games in order to stay correct and to have a smooth project. But then one of the aspects you can that often comes up is gonna be color theory, especially because of course you're gonna have colors in your game, and color theory is about how the aesthetics, so more the feelings that it evokes, and the communicative qualities of the colors. Because you can see color as different things. Like you can see it with the dry definition of the technical definition of hue, saturation, and value. Or if you're on the computer, more specifically, it's gonna be red, green, and blue, because it's because of we use additive light with screens, whereas it's cyan, magenta, and yellow. It's like, what's the English word? Yeah, yellow. For printing, because it's subtractive instead. So this is the technical way, but you also have the aesthetic aspects or the symbolic aspects, even we have a red or blue. Like you have those hot colors and cold colors that give different feelings. You also have the communicative abilities. For instance, where green usually means go, whereas red means stop. Or even in games more specifically, health tends to be red, while mana tends to be blue. Stamina tends to be yellow or green. That, but mana can also be green. This is part of communication, and you also have the symbolic aspect, like yellow is joy or something like that. You can use whatever you want, of course. That's a guide. But especially what's really important about colors is that by themselves they don't really mean anything. They don't really give anything. It's through combination that they really take on meaning and aesthetic parts. Because because we don't really perceive color as the global color itself, but as through its relationship with the others. Just like when you're in a night scene, it's everything has a bit of a blue tint in general when you draw it. But you can still, even when it's very tinted blue, you can still feel what is red in that part, even if the color isn't actually red, but it's just like a very dark green, for instance. It's because of that relationship with the other colors, you are able to give that one meaning, to give, for instance, that, oh, this one is red, or this one is in the shadow, even if it's the same color as something else that's not in the shadow. So, of course, you also have like which colors go well together. So with which you can find also through methods of making palettes, like with complementary colors, like red's complementary is cyan, and you can create palettes that way. For instance, with a split complementary, like you take red and you take blue and green as a. I mean, you take a slightly green cyan and slightly blue cyan, and that way you get a few colors that go well together. One other way is to take I think they call those triangle palettes. You take 3 colors and you just mix them together in order to create the ones you want. So the space of color is called gamut, I think. Maybe I'm just using the French word, but it's we call it gamut in French, but I think no, it's an English one. But yeah, the color gamut. Yeah, I'm pronouncing correctly. The color gamut is the ensemble, the set of colors you can use in your painting on in your specific scene of a game or something like that. And you also use that for screens and stuff like that, but that's a lot more advanced. We're gonna talk about it in the rendering part. But yeah, and you have the composition, like how do the colors and composite on your scene, and that's where the eye will be able to be pulled towards. For instance, like with the 2 colors that clash next to each other, will bring the eye to it. In fact, like it's one of the tools you can use is to go into grayscale and to see just the value of the colors. So that's a bit simplified, of course, but yeah, and that way you can see, like, does my foreground elements, my gameplay elements, pop out more than my background elements? Is the contrast right? That way you can, if the eye is driven towards a specific part of the screen, is it the one I want to bring attention to? So that's it's not just like in paintings, where you have to plan all of that also, but it's more static. You have more time. In games, you usually also have functional elements you want to bring the attention towards, like the characters, or as part of the environment, depending on the type of game you do. So that's something you have to keep in mind. Yeah. So, on the more technical side, in order to use like 3D graphics, we have 2 ways, but so raster graphics more specifically, it's we use what we call sprites. So a sprite is a 2D array of pixels. A pixel being short for picture element, and it's a tuple of red, green, and blue, because these are the colors the screen actually outputs, and sometimes alpha, which is a transparency, or it can be an identifier which is useful in the case of old games and indexed palettes, where you say I want color 5 or I want color 2. and you use them through what we call blitting, which is an operation where you copy the pixel on the screen relative to a fixed point, which we call the anchor, or sometimes it's even the origin. So because our sprite array usually starts at the top left, position 0, 0, but oftentimes it's not very good. For instance, if you take use spritelet, let me actually get a small drawing up. So like if you take a sprite, like you take a dude here, like that. You take your dude, he's that. So the technical origin is always gonna be top left because that's where the array starts, and you get another sprite that's shorter but longer because now dude is giving a long kick. So so that's the issue here. So if both are here, you want to put it in a position. However, if you set where you have the ground here and you put your guy here, you just manage all of that. So first of all, his position on the ground is not gonna be here, it's gonna be like here. So I mean, if you no. Usually you have your position on the ground, and that means you will be under the ground. So you want to be able to put that guy above it. So that's why you use an offset. And the offset is actually the anchor. So usually you tend to put it towards the feet, in the middle, or in the center of gravity, depending on what you do. But for instance, in platformers, you want to put it towards the feet, usually. And that way, you have this offset, and you can reapply that same offset here, and that allows you to put your character exactly where you want. And that also allows you to change depending on how big is your sprite, because I can put my anchor here, because otherwise my guy will be floating if I use the same one every time, and that means here it works. But if he was putting the leg backwards, he will be bringing himself forward with that move. So instead, by also having an anchor here, I can also keep him grounded in the same position when he does the kick. That's something that comes up quite often, and that's what we call the anchor. So the sizes are also often gonna be powers of 2 for performance. So that's on the GPU end. And you can also apply what we call transformations to them. So that's a mathematical term, but that basically means moving around, rotating, scaling, all of that, shearing even. If you play some old games, you can see like for instance SNES with Mode 7, you can see they tend to use that a lot. And you might also see like it's not the results you get with Mode 7 are very different than the ones you get with, for instance, Flash sprite animations, which is because those are actually a question of signal theory. We won't go into very much detail, but basically, like, because you need to resample your new sprite on a new grid, and Flash animations usually have higher resolution, so they can actually take all of those big pixels and still show them as big pixels, where the other have to resample within that. So let's see an example, for instance, here with a scale operation. Depending on how you do your reconstruction, which magnifier you choose, you can get either the result on the left, which is simply nearest neighbor. They take the nearest pixel in order to give that. So that's why you keep the exact look of it as it goes bigger. This is linear interpolation, so you can see it's smoother, a lot smoother than that, but you can still see the traces of the pixel, like here on the oh, I forget my English. Whatever. Here towards the head, you can see it's a bit square. But if you use other filters, I think this one is Sync, SINC, which is a lot more advanced. And you see here, you also find the round shape once again. But it's still a bit limited, of course, a bit waxy. Right. Let's see, that. Forehead, yeah. I had to Google that one. Come on. I lived in America, can you tell? But yeah, anyway, oftentimes you might want to do pixel art, because if you do 2D, you can either do like big drawings, which is nice, but oftentimes you also think of pixel art, which is a style that comes up quite often. So this style was usually based on platform limitations. Right now we don't have them as much anymore, but in order to really understand what makes it tick, you need to get into those limits. For instance, if I take the Game Boy Color here, it has a more limited resolution, so of 160 times 144 pixels, which is quite low compared to the ones we have today. And you also have limited colors, not even the 1.6 or 16 million we have now, but with full colors. But it was also limited there, and you couldn't get any of those 32,000 colors. You had to choose 56 through the palettes. So because because sprites worked as tiles, of 8x8 or 8x16, and they needed to be assigned palettes because they didn't have enough of that. And a palette is a 4x4. No, it's a four colors that you use for an 8x8 tile, or 4x4. I think it's 8x8 for Game of Color, and all of that, of course, has a cost, and that means also that your 56 is the maximum theoretical number, because in practice you're not getting all of that, because one of those colors because you're gonna repeat colors, and oftentimes one of those four colors on your sprite palette will be transparency, which means you don't get that many colors in actuality. You also have different modes of rendering for either sprites or backgrounds, so that's each one at the limit, so you had to work with that. You also had other restrictions, of course, like the number of sprites per line or per frame, or the memory in general you had. So, all of that brings some restrictions, which is reflected in the sprites they chose and in the way they are built. So that's and in order to make appealing sprite art, usually you need to also think of those limits too, because instead of just drawing something quickly, they had to go over it several times. So, of course, that you can go a lot deeper than that, but let's keep it fast, because there's also another type of way to make, on the other end, instead of doing like drawings in directly like that, you can also use what we call vector images. So this is opposed to raster images. Raster images is the kind you do know. It's the images that are made in grids. So all of those pixels on the screen, this is raster graphics. Vector graphics are not defined by just a grid of pixels with colors. It's actually a list of shapes, which we call primitives usually. And the thing is that instead of, when you want to render it to your screen is raster, so you have to go through a pipeline, through an algorithm which is called rasterization, in order to go from those vector drawings to a raster drawing. And so that means you have to you can get it for whichever resolution you want. It has perfect resolution. You do a circle in a vector, and you can zoom as much as you want on it. It will still be perfectly circular. The thing is that you have to compute it, so it takes some time on the computation end, but that doesn't mean it's gonna be a problem, because you can also pre-compute some of them. For instance, one thing that's very good, for instance, for UI icons. You can create your icons in vector graphics. Hello, Migui. So you can create your icons in vector graphics, and then you can pre-render them. You can bake them into pixel into raster graphics or of specific sizes, and that way you do get the advantage of being able to resize it later if you want. But you also have the speed of raster. So let's get to 3D now, which also works through that, but we're not gonna go into the details of exactly how we go from because 3D is also vector graphics, but we won't go into details of how it goes to raster. That's the rendering class we have in a few months probably. And so today we're gonna see more about what's happening for 3D, because it's a bit more complex, not just a drawing. So you have for the step of 3D modeling, you have a few things going on here. So we have a few definitions. So we have the mesh, which is a graph of vertices assembled as faces. So the computer is always gonna see them as triangles, but it can usually be like quads in your what we call your DCC, which digital content creation software. You have the materials, which is the surface rendering parameters and the data that's associated with them. So for instance, the texture of that. So that's what makes your surface look metallic or wooden or whatever. You have your 3D model. The 3D model is actually just the mesh, the materials, and the associated data with that, which is the rigs, which allow you to move the model, and the animations. And then all of that, you have a 3D scene, which is the 3D models, plus the lights, plus the camera. And once you have the 3D scene, you can actually render it on the screen. So I put one images for instance of here in Blender, but because this time I'm not in a class, but actually on my computer, I can also show you just here, like I was working this morning on making some the sprites for Molten Winds. So I can show you directly what is a mesh directly in the engine. So for instance here, that one's very simple, not my best work of course, but you can see like you have those vertices. So this is the mesh itself, is the assembly of the vertices. You see I'm having quads, but the engine doesn't see them as quads, and that's a bit obvious if you see it. If you use the flat shading, at one point you can kind of see sometimes where it goes from one. You see like here, because quads can't be always planes, you know. This is not a flat surface, a flat quad. It can't be flat. So you see there is this edge because the Blender use this triangulation here. Like this is the actual triangle we see. Like you can see it doesn't change the thing. But if I tell it to do in another way, you'll be able to see that now the silhouette has changed. Because the advantage of triangles is that they always are planar. So that's why the engine integrated it. But if you have quads, it's also better for topology because it can understand operations like this is a strip. Whereas if you just had a triangle strip like this, for instance, this might have been harder to parse. But yeah, so this is the mesh, and this is the material it has, which tells it how to render. So what color does it use? How does it react to light? For instance, I can change the highlight size here. So this is, of course, this is stylized rendering, not regular rendering, but you know that's still the same concepts apply. So you know, like here I got a big highlight here and a bit of mid zone here. You know, you can do a lot with depending on how exactly your thing is set up. Of course, like if I put a couple parameters here and dithering, I can even activate like dithering on the material. That's how I render the surface in order to make, for instance, the highlight a bit smoother. I can use that, and that's on me. That's the material. It tells me how to do that. Textures are also used here. I mean, I don't use textures, but I mean that's where they also happen. So you can see a bit better. So what does so of course I say the material, but how does it work in practice? Well, the color of a pixel, each pixel's color must be computed, and because at this point in the rendering we know which object is in which pixel, you have to compute every color like that, and you can use the material of that pixel. And this is done by a shader. A shader is just a program that runs on GPU, and a material can be seen as a shader and its parameters, which can be a texture, can be all of that. So, and here, well, my code here tells me, yeah, well, look at the light, and if it's lit enough, well, use the lit color, otherwise use the shaded color, you know, that kind of stuff. So something that's coming up very often in video games, and especially since the last 10 years or so, we have has become the standard, which is physically based rendering. So instead of the idea of physically based rendering is to be closer to reality, not photorealistic exactly. It's close enough, for video game it's close enough. If you go into my lab, it's not close enough, but we have people specialized in exactly capturing reality. But so it's close enough to realism for us. So physically based rendering is based actually not on just your eye, like, oh yeah, this looks lit enough. It's based on actual physics and measured and measurable parameters. For instance, instead of having a color like I used here, you have the albedo, which is the color of the object under white light. So that has specification. You can go there, you can take an object, you can put it under said white light, and then through a photo you can get the actual albedo color of that object. That means you have the actual rendering parameters. And because we use physical formulas, like it's not just, oh, I have a light of strength 10, it's I have a light of 30 watt, for instance, and it's and the temperature this much, I don't know, 5000 Kelvin, I don't know, I don't use those values, but that way you can actually get the almost the same render through different engines because the parameters map to the same things. You also have other parameters, of course, because all of that comes through what we also call a BRDF, for bidirectional reflectance function, which we'll call about more in the rendering part. But that's basically the exact algorithm you need to use to do that. But it's also a function you can measure in real life with an object called a reflectogoniometer. Let me I took out the page. Let me get. Let me see. Let's see if we have one. But yeah, a reflectogoniometer is an object. We can. I couldn't really see that part exactly, but basically, reflectogoniometer is a table with a light and with a camera and a light that comes from different angles, which is what it means, like reflecto for reflection, gonio for angle, and meter for the measure. But yeah, I think this one is actually one that's more standard. But yeah, so that's so you can actually measure a lot of parameters like that, and that way you can get very, very results that are very close to reality. So that's one, and this has become pretty standard in video games because now all of the pipelines use that, and especially use what we call the Disney BRDF, which is not made to be always 100% of the time photorealistic. For instance, the metalness parameters, it can be between 0 and 1, but in reality it's either 0 or 1, but you can stylize it a bit. That. But yeah, there's some limits. It goes a bit further, but yeah, a material is how the surface looks, and that's given by a computer program. So you can do a lot of very funky stuff with that, like what I did with the dithering, for instance. That's simple, but yeah. And you have textures. So how do textures go into that? So a texture is, to simplify stuff, a texture is an image applied to the mesh. Because you have because you usually have 3 scales of detail, in rendering, which is macro detail, which is several pixels, and this is usually given better by geometry, like the mesh itself. You have sub 1 pixel parameters, which is usually given by a shader. So what is sub 1 pixel detail? Well, for instance, in order to render some materials correctly, we have to go into what we call microfacet theory. Well, we say that every object surface is not smooth, but it's actually a lot of small, almost not mirrors, but small reflective surfaces, one next to each other, that reflect only a part of the light and reflect between them and hide one another from view, all of that. And in order to do that, we don't model all of those micro faces by themselves. We actually use a statistical model through the BRDF, so that's only in the shader. But you have what we call mesodetail, mesogeometry, which is then it's the exact size you want to use textures for. It's too small for it to get like good geometry performance, but too big to get actual micro detail, and this works well. So usually you apply a texture via UV mapping, where every vertex of the mesh points to a point of the texture. Like if you take this example, once again, you have the mesh of the dragon here, and when you apply the texture to it, you get the colored dragon, like with the wings, the horns, the body itself, and you have the texture next to it. The thing is, it's like like if you with paper cutouts or when you do a dice out of paper. So that's exactly the same thing with patterns. So the thing is that for each point on the mesh, like for instance this point of the wing is actually hold some extra parameters, which here we call the UV, because you use the U and V, and you can see like this point is exactly here. So this point and this point is here. This point is this point here, and when you go between the two, it will interpolate between those two positions, and that way that gives you like the color of this pixel, the color of this pixel, but you get also all the ones in between automatically. And same, you go through, because it does that with the whole triangle, so you have the triangle here, and it's this triangle here, so it also merges all of that data once again. And you might have seen like we have two wings on the dragons, and you have two sides, but we only have one here because with that system we can also reuse those parameters several times. Like here, the mouth has a non-symmetrical texture, but the two wings are symmetrical, so they just this point and this point both point to this specific point here on the texture. You can do that. There's no problem with it. And doing it that way actually gives you more space to work with your texture, to put your data. So that's why it's always good to think about the technical aspect. But yeah, and the texture can not only hold colors but also parameters. You can hold, for instance, all those roughness, metalness, even ambient occlusion. We didn't talk about that, but whatever. But these standard parameters, they can also be held in the texture. So instead of having just one texture for your character, you have your ILM texture or your metalness, roughness texture. Your normal texture sometimes, often actually. Yes, and holding different data in textures usually is more of the domain of tech art. So we won't go into too much detail here, because it's gonna make a lot more sense when we talk about rendering. But actually, this part about the normals, I'm going to go a bit further on that because it's actually quite important and shows you the idea well. It's what we call bump mapping or normal mapping, depending on the exact method, but it's the same thing globally. Is to add fake geometric detail just for lighting. So instead of having like a flat surface, you make it look like it's actually full of detail. And for that you use a height texture or a normal texture. So height, of course, that's understandable, but a normal is the surface direction, like a vector perpendicular to the surface. Like if you take a flat table, the top of the table, flat, and its normal vector will be towards up. It's like if you try to put a thumbtack on an object and have it rest on a flat part, and you see it and you see where it points to. So let me give the small drawing once again. Which with the previous, I think it showed. But yeah, if you have a table, like this, and if you take the top of the table, the normal vector looks towards here. On the side of the table, it's towards here. Here it's towards us. As you say, like if you take a sphere, well, the normal vector at this point is gonna be away from the sphere. It's always gonna be away from the sphere, but as you can see, the direction changes a lot. And if you're more towards the center, well, it's gonna point more towards the camera, so you don't. Whereas if it's on the side, it's gonna be perpendicular to the camera. But yeah, you have that's the idea. It's a bit technical, but the idea is that you can, instead of leaving it through the geometry, you can give it through the textures. and that gives you the illusion of a smoother surface. As you can see, here is a height texture with which part is higher, which part is lower. With I think the white here is lower, and if you can see here, like, yeah, we have the light and it shines through, and you can see, like, oh yeah, this part is lit, this other side is not, whereas the geometric model itself is just a sphere. All of that is illusion we obtained through the shader. You can actually see that a bit at grazing angles. That's where the limit comes from, because this is, of course, like, the object doesn't change, the geometry doesn't change, just the light detail. So when you go here, you can see it's not a bump here where it should be, because this is limited at grazing angles. You prefer other methods like displacement mapping, which actually create geometry, and but those are more costly, of course. You don't often create those textures manually. You usually project them from a more detailed model with what we call the sculpting workflow. I will talk a bit more about it later. But yeah, when you combine all of that, you can create some pretty complex materials, like here. You see, we have for instance, this brick texture we applied on this is actually made from an albedo texture of the bricks, which is, well, just the color, as we mentioned earlier. You also have the roughness, like here the roughness given in the texture, so that means that the cement doesn't reflect the same way as the bricks, Here the bricks, because it's more black, it's smoother, so you can see it reflects light a lot more directly, whereas the cement is very rough, and that way it doesn't reflect light as well. And that makes a more complex material for very little cost, Same for the height fill textures. That way you can also use the height, to vary a bit the color inside of the brick, by having the light be a bit die down a bit more here. But yeah, so that's very interesting. But if you want to go to the other way, like what I just did before, I showed you before, is by using, for instance, toon shading, which is stylus shading in general. You usually want to limit shading, you reduce shading to limited tones, like they did in cellular animation, where you couldn't get like any kind of color whenever you want. You only had some limited ones. So you said, okay, this is my lit color, this is my shaded color, and you use them. And in order that you do toon shading, you often, with cel shading, you need a function that allows you to do so. So often with what we call a lighting coefficient, which is basically how much your object is lit. And a toon ramp, which you might have seen, is a way of storing this function instead of a texture, instead of just math. Of course, we'll talk about this more for more complex subjects, but I also released an article the other time on my blog, panthavma.com, on toon shading. It should be the second to last one that I released. That actually goes into a good introduction on the subject, that goes in depth apparently more in depth than a lot of other articles, from what I've been told, but yeah. But I think it's, even if it's limited somewhat, it goes in more detail. And that way you can see, for instance, here, the green channel here, it's it does give the green channel is our lighting coefficient. As you can see, it goes from red to yellow, depending on it. And at one point, I just put a threshold, and that's where it happens. You see the shading is now separated in two. That's how you can do it. So yeah, of course, then you also have another part, which is a bit between the animation and the model, which is how we can make our model move. And we're gonna do this through skeletons, so skeleton-based animation. That also exists in 2D, of course. So a skeleton is a bone hierarchy, and you can use that to move your model like a doll by basically putting some bones where you want. Actually, I'm gonna show it through here directly, once again. So each of those things are bones. Let me show them like this, it's gonna be easier. So a bone is made of so you have a hierarchy of bones, so that means the torso bone, the head bone comes after the torso comes after the waist, So when I've moved the waist, I'm gonna move all the rest I'm also gonna move the torso and the head. Then I can move the head separately. The idea then is, how does each part of the model get together, Why does it know this part is the head? That's through what we call weight painting, where basically like if I take my like 3D model, I told it, yeah, so this part is actually this vertex goes with this bone, and this allows me to make my to make it work correctly. If I put it into weight paint mode, you can see this is how much it's affected by the head. If I make it move through the torso, you know, I can paint my model in theory. Oh, well, I painted the backside of the model, apparently. You know, as you can see, I'm not really using that too much, but for instance, here you can paint the weight of the model, you know, or because here it's rigid transformation, I just gave it a value of 1 for the head, you know, and be done with it. But you can use several vertices and different weights, you know. Here it's 0, but here it's a bit more, you know. It adds up a bit, and it does a mean. That means when I move the head, it takes the mean position between the torso bone and the head bone, which allows me to do this, which here in this case it doesn't work because it's not logical here. But for elbows, that's very useful. For instance, you have the elbow is affected by both the arm and the forearm. That's where it's useful. In most cases, in game engines, you only keep one. You only keep 4 bones at most affecting a single vertex because it's also expensive to compute. But yeah, and once I have that and the other, I can now move my model however I want, you know, and put it in any kind of pose, you know, in order to strike at people. But you might have seen, like, there's of course there's always something more, you know. If you just do it like this, you know, you have a skeleton. I move each bone separately, like here, the torso, I move the torso, then I move the arm, then I move the other arm, you know, to put it where I want it to be. So that's cool and all. However, this has some very present limits into how I can use that. Because, like, for instance, if I wanted to have the character grab an object in front of it and bring it towards them, I will need to do so. I have this pose right now, but then I will need to manually move that object and move it here, and that's gonna make some really robotic animation on top of being hard to compute. That's why we also have this is just a skeleton, but when you add some more advanced controls, like what we call inverse kinematics, it becomes a rig. So inverse kinematics, what we just did is forward kinematics. You start from the root and you go forward until you find the final object. Inverse kinematics is you start from the final point and you find the correct rotation of the bones to get there, which allows me to move my shield, or my arm more specifically, very smoothly. Like I just put it where I want. This is very useful for feet especially, because here I'm on flat ground, and that means I can move my waist and still stay on the flat ground. You know, I'm not clipping inside of it. Which is why sometimes, you know, we can also apply those in real time, because rigs usually stay in the GCC, and they get pre-computed inside of animations that I can then use. But sometimes you use the inverse kinematics in actual gameplay, for instance, on the feet especially, in order to, if you are on the slope, for instance, you can put the second feet here, and you can override this part of the animation. So now, you know, you can do the same animation as before, but the leg is in the correct position. That's why also sometimes on stairs you can see, like, the leg do something like this, because the point is moving a bit too much. But yeah, so that's when you get these types of controls, you see, and also I can choose between forward kinematic and inverse kinematics. That's where you go from a simple animation, a simple skeleton, to a rig. And a lot of rigs have more advanced control, so I can handle a few effects from here, you know, like with some vertical effects, or to hide some part of the model with the screen. The screen here. Oh, here, I don't have a lot with this one. This one doesn't need too much. Like even the flate doesn't have. But let me show you actually on the Emblitz model. This one takes a bit of time to load. But for instance, here that's what I use for Conan Titans, which you might have seen. And the thing is that it also has like inverse kinematics and stuff, but it has a lot more automation and helpers For instance, here when I move the leg, you can see like there's the armor plate here actually moves with the leg. That's automatic through the rig. Here like just this part. You see like the armor plate and the piston behind it. They move. I'll show it in color. It's a bit slower in color. You can see like you see the piston behind it actually pushing. And I also have like controls, for instance, for the weapon. Like for instance here the rifle, it has it's very animated, but I can with one control I can deploy the rifle itself, and through only one of these I can also control all the rest. That's with that's some of the things you can do with rigs. So that's of course a bit. I don't think I'm doing anything very very complex here, but that's all for the arms, for instance. Here you can see there's it's separated into a lot of different motions. Like all of these parts can move independently from each other. The idea is this one only does one axis, this one does another axis. Not this one, but it doesn't move, of course, because they have the schematics, and it decomposes the motion automatically in order to respect this joint structure and do a higher quality animation. That's the kind of automation you can add to your models, which makes them easier to use for the animator. Which is why usually it's someone that does those, that is separate from the modeler and from the animator. And this guy is called the rigger. And it's one of those more tech-arty jobs. But yeah, it's always useful to have one on your team. So, of course, I had this old prototype that was before Conan Titans at all, so that was just general test I made. But yeah, same thing, the pistons also works automatically. But yeah, so now let's talk. Is it good for now? By the way, you can always ask questions in live, and it's not an issue. I answer when I see them. But are you able to follow correctly right now? So it's not. Oh yeah. Don't hesitate. Okay, so far perfect. So yeah, how to integrate that in games? How did you integrate it? So the thing is that you have to start with a pipeline. So not to start with a pipeline. You have to find a pipeline during your pre-production time, which is the list of steps and tools you need to make a character or object or whatever. So I'm going to give you a standard one, like what we call the sculpting workflow, that usually works. You can give separate parts to separate people sometimes too. But the idea is to start with the drawing, like what exactly you want to make. So usually with a concept artist, and you want not just drawings, but usually like reference drawings. So instead of having like I have this cool Blitz picture or whatever, instead of that, I get my actual front view, side view, top view eventually. Like made by the artist. It's not gonna be perfect, but it's gonna help you a lot to position the things exactly how it's supposed to look. So you want this kind of thing, but you also want your regular drawing, to be able to get the vibe, And then you create your high poly mesh through sculpting. So sculpting is another way of working. Like here, I showed you the more direct vertex placement style of work that I tend to use, but a lot of artists in the industry use sculpting, which is you take basically like a clay ball, and you change it, you pull it around, all of that, in order to get the shape you want, and then you get more and more detail on that. You sculpt that detail, kind of like doing a sculpture in real life. If you had like a weird infinite material, you can always move around, and that way you get your mesh with very high level of detail. And from that, you also create a low polygonal mesh that can actually run into the engine, and you project that one through what we call baking. So that's when you take, and this is what will create your albedo texture, your roughness, and all of that texture, and the normals, especially the normal texture. That way, you can fake that high level of detail you created in the sculpting phase through bump mapping or normal mapping like we saw earlier. So at this point, there's someone that takes you can give that work then to someone else that will create the materials and the textures for each part with other software usually. Like for instance here, if I'm using like the industry standard, which is going to be proprietary stuff, I don't tend to recommend that usually. But yeah, so if your high poly mesh or low poly mesh will be created in so your high poly mesh through sculpting will be created in ZBrush, for instance. Low poly mesh in Maya, which works very well with ZBrush. Baking with another software like Marmoset or Marmoset, I don't remember exactly. Then someone else creates the materials and textures through Substance Painter, or Substance Designer. Then you go back to Maya or do it in the parallel, and you create the rig and the weight painting. And then you have an animator created in Maya once again. If you use Blender, you can use Blender for pretty much any of those steps actually. Though the materials and textures, usually it's gonna be harder. Like sculpting is not as good in Blender as in ZBrush, which in general Blender is pretty good in all domains, but it has two weaknesses two main weaknesses that get it beat as well. But yeah. And so the materials and textures, actually I think there's something called Material Maker that is made in Godot actually, and that works pretty well from what I've heard. I don't tend to use that's not my own workflow. Like my pipeline, as you can see, as you saw in my in my showing, just doesn't look like that at all. Like I just do my vertices one by one, on my grid or whatever. I put them here, and then I don't use even any texture. I just give it a material ID, and I just use then my color parameters, which are towards here. Like this is one. So I put the main color, the shadow of that. This is the way I work. You have a lot of different pipelines, as much as projects, but you have to. And this is actually given by another role we didn't talk about, which is the technical director, which is the one that actually gives you how much you can put in the game and stuff like that. So let's give a few examples, not just mine, but for instance, you can use it in both ways, either for 2D or for 3D. So for instance here, BlazBlue used a lot of 2D sprites, but they started with 3D models first. Like they had their concept drawing here, but they did a 3D model of that in order to have the proportions correct and that stay correct between artists, which is a big part. How do you stay coherent between different artists? And they had the model here with the colors, the color map for the object, and you see like the shaded parts and whatnot. They also have this shading idea, and then they reproduced it manually. Instead of baking that detail into the model, they said, okay, I'll do it by hand. Now that I have a big reference for the actual look of the sprite itself, I can now shade my model as expected. Then the other way around, like the team at Motion Twin, no Evil Empire, Kenda, made Dead Cells using 3D objects, and then rendering them automatically as pixels. So and that also allowed them to export the normal map automatically, on top of being able to adjust the speed of animation and keep very fluid animation. They are able to also keep that lighting detail, and in order to make cool dynamic lighting effects live. Another example is what I do here with so it's another screenshot, but for Molten Winds, same idea. Instead of here, I'm not keeping the lighting detail. I'm using a bit more advanced algorithms in order to have my my lines, especially. Like I wrote a full article if you're interested, but you saw what it meant. Like it just through that. Once again, that's actually a good example of what we talked about earlier. It's once again a question of technical direction, which took into account the fact that I don't have time to do all of those sprites by hand, especially if I need to adjust. Like that's not all the sprites it uses like a lot. Like for instance, physical attacks. You can see all of those images I made. So in technical direction, I'm trying to evoke some aspects of the style by adding some arbitrary limitations to myself. Like see here, there's only limited animation, so I don't actually use all of these frames. Actually, I render them, but in the end I saw that the animation looked better with fewer ones. But you see, I used limited animation of just this part because that's what an artist will do. Even if I could use 3D to make like very smoother animation, if I did that, it would really break the style. You know, say I have and this allows me to really adjust the animation. Like if I don't like this one, well, I can just move, for instance, the shield here. Maybe I like it more, and then I just press F12 and render it again. You know, bam, and I get my sprite ready to be made, put in the engine. You know, that's a way to use the technical limits and the artistic ones. Same thing and that way I also had to choose my controls, exactly which part of the lines of that. And that also allows me to work with the sprite palettes directly. But yeah, so that's how you can use that also to speed up your own process when doing games. It's very wide, you know, and that's why you have to keep your technical part in mind too when you do all of that, because it has to be put in the game at the end, and you have to make it. So that's what I meant when I say like production limits and technical limits. Like here I don't have a lot of technical limits, but I have a lot of production limits, and I'm adding some fake, not exactly sure technology limits in order to nail that pixel art style, which you can say if I nail it or not. That's another question, of course. I try to keep it. It's not a hard limit. I took a bit more in the article. It's not a hard limit, just to give an idea. But here, for instance, this sprite tends to be very, very too much detailed. Here, a lot of colors. You know, I'm kinda abusing that system. You know, even if I try to keep the colors limited, for instance, here, you know, there's the green parts only. I removed the highlight so you can see it's only 3 colors here. I used 2 at first, but it didn't look really good. But yes, that's how to evoke that and not actually follow. It's how I am able to finish a character like this in I don't know how many hours this is, but you know, it's to create all of those animations by hand will take a lot of time. So using 3D helps a lot here. And even if you take like the high-end rendering route, it's always there's always choices to be made. You know, even in the big AAA games, we also have to make choices on what parts of rendering do we put more emphasis on. Do we put more emphasis on the lights and stuff like that? So that means we can handle more expensive light computation. You know, do we put it more on the models, on the textures? You know, there's a lot of aspects that come even high level. But yeah, so of course, yeah, you might have seen all of that. You might be either like, oh yeah, that looks so cool, I want to do that, but maybe you're like, oh, that's absolutely not my thing. So you know, because it's games, you always have ways to avoid, and just like, you know, people can avoid doing programming by using more pre-made engines and stuff like that, you can also, without speaking to a programmer or an artist, you can also use a few tricks. One of them is using an art pack, like, you know, you have Kenny or an open game art. You know, you can find a lot of really good sprites and assets and 3D models, all of that. So you have to dig a bit more for them, and the coherence might not always be there, you know, because for instance, all my Molten Witch sprites are the same style because I made all of them, and so they are coherent with each other. But if you take like random assets online, you won't feel that way, you know. So that means you have to choose them carefully, but you can also use them as a base to edit. Like for instance, you found a cool Minotaur model, and you can tweak it a bit and make it a bit more demonic or something if you're doing a demon Minotaur, I don't know. And that way you can get that coherence from with a lower effort. You know, you're more limited, but you might have to be a bit creative to work around those limits, but you can absolutely limit that part. Or you can use less complex style. That's what I meant also about designing a game around also your limits. So mine was creation time, but you can use less complex style. For instance, the old classic, the terminal games. For instance, roguelikes. You know, a lot of them use N-curves for rendering, which is just letters in the terminal. You can use low resolution pixel art, some people also do that to allow them to make more animations. Like if we take for instance the indie game Crawl, which has very low resolution pixel art, but that allows them to do animations that are a lot more fluid that you can usually afford to do with higher pixel sizes or sprite sizes. Sorry. You can also try low poly. You can try a few things. What I did once again was in my own project I tend to focus more on shader detail because that way I can spend less time on the actual textures especially, but that way I can just focus on geometry and my art style engineering reflects that. You can work with what you have, and sometimes maybe work with someone else too. That also works. But yeah, so that's about it for today. So we saw the basic concept as well as how it works in 2D and 3D. So on the side, you can try out to make some 2D and 3D art. Not necessarily on the computer. You can just get a pencil and draw on a sheet of paper. That works very well too. You can also try to define or analyze an artistic direction for a game you make or a game you like. Usually I give you software at the end. So in this time, once again, I'm giving you a lot of software. So yeah. So for 2D, it's a bit more wider. So GIMP does raster graphics. It has some limits. People usually tend to use Photoshop a lot more for various reasons. GIMP works well for photo editing, but also it works for. I find it works very well for pixel art specifically. This is the tool I prefer. Inkscape is for vector art. Like it works very useful for vector art in general. So if you like that kind of workflow, you might want to look towards it. Krita is actually what I use when it's this software here, which works very well if you want to do more traditional drawing, especially if you have like a drawing tablet, like well I do now. I didn't have at first, but you can see, like, for instance, with a pen you can get different amounts of line weights and stuff like that depending on how much you press with it, which allows you to make more expressive parts of style. Because you can do more easily like your sketch designs. You can see I'm not necessarily an artist, but for instance, because for line weight can be very important depending on what you do. Like this part can be more emphasized by the line weight, while others can be made less visible. Like I can bring some attention to the extremities here by adding more weight on the line. It also shows a bit more of the human side of drawing. But yeah, so that's you have a lot of options with it. I'm just scratching the surface with that, but there's so that's an example of what you can use for really more drawing type sprites and stuff like that. For 3D software, I have to recommend Blender wholeheartedly. So you might have heard, especially with the years before, like people said, yeah, Blender is very separate from the other 3D softwares, which is true. It's true. It has a very different interface. So usually either learn Blender or learn Maya and stuff like that. But you had a lot of people trying to gatekeep, especially then, because all those kids that learn Blender separately. Well, first of all, a lot of the skills do transfer over, so you don't need to worry about that. But now the tables kind of turned a bit, because Blender was good, but it becomes better and better as time goes on, and the other softwares kind get with the problems of subscription and all of that. And the thing is that with the recent interface ameliorations, it became a lot easier to use too, and that means that now, especially in game dev studios, you are not always forced to use a specific one. We have, for instance, at Ubisoft, we have a lot of we develop tools for each of them, so that artists can use the one they are most comfortable with. And of course, Blender Blender has strengths and weaknesses. So, for my opinion, compared to the other ones, it's the best overall choice. So you're not really shooting yourself in the foot by using it. It has two major limits compared to other commercial software. it's the sculpting workflow, which is a lot better in ZBrush, which is specialized on that, and that's why it's also often used because it's very strong. And you have like procedural modeling. It's good, it's there, it's starting to get a lot better, with geometry nodes, so that might need to be updated in the future. But but it's not at the level of Houdini, for instance, which is used to make procedural geometry, which is basically instead of saying, I want a couch, make a couch, with the, like this, you have your simple couch. Instead of making it every time you need one, you can make a sort of couch maker. Like instead of having all of that, you can give it the length of the couch. You give it the armrest length, and that way you can automatically compute like, oh yeah, so the thing is here, the thing is here, so you can create those armrests automatically of the length, and then you say, oh yeah, so this length is so much, so that works with 3 cushions. So you create those 3 cushions of the exact size you need automatically, and so that way you have your couch generator, and you can put it. You can put exactly the one you want in the environment. This is very useful for buildings, especially. This is the kind of stuff that Houdini does a bit better than Blender. You can also bake, like for instance, wind into sails or stuff like that. There's a lot of stuff to learn on that domain. Blender's big advantage compared to others, actually, one of the fields that it's very relevant in, is stylized rendering. Because not only is the whole community around stylized rendering tends to be around Blender, because it's usually not the big studios that aim for that. It's more the scrappy guys, so they tend to use the free tool. But it also has like very good tools. Like if here same thing here, like I use it here, and you see I have this whole rendering engine, which is called Malt, which allows me to really control how the rendering is done. So that way I can put my material exactly how I want and create my exact render from here. In this case with code for me, but you can use other ways. But yeah, so I recommend Blender. What's something I will tell you to do, like if it does ask you at startup, but if it didn't, like you go into preferences, and you want to activate. I always forget where it is. Navigate. No. Keymap. In Keymap, you see, so selection button, that's the one you want. I'm a boomer, I started using Blender in 2004, so I use right click select. But what you want is to activate for the spacebar action, you want the search one. That's the one I recommend most of all. So you have a few other options. I tend to like these ones too, but that's about the only thing I change on my Blender. You want that because Blender has a lot of functions, and a lot of them are not accessible easily through a menu. Like this, it's very slow. Instead, you have a lot of keyboard shortcuts like G to grab an object and move it, R to rotate it, S to scale it, or W to add to start the pose context menu, because I'm currently in a 3D view and in pose mode. Because Blender works with the kind of view you are in and where is your mouse. Like if I do it G here, it grabs this part to move. If I do it here, it grabs the whole keyframe. Like it grabs the keyframes of the shield. So that gives me the shield's position in different animations. Same for if I took the torso. Like you can see the torso moves a bit depending on which frame it's in. So of course, so you have to be in the correct position to use the correct shortcut, and that can be a lot to remember. But if you have spacebar search, you can just write whatever you want. Like for instance, I search for shade flat. It doesn't work because I'm in pose mode. But yeah, if I'm in edit, if I'm on the mesh actually, and I say shade, I can see object, shade flat, shade smooth, all of that. If I'm on the face like this, I search shade flat, shade smooth. Here once again, and I can see also the keyboard shortcut. So Control F, damn, I got it here like here. I can see which part is here. same if I do Shift N, I can compute the normals of my object, because sometimes it's because sometimes they came out wrong. So I can recompute. I can all of those functions that are useful, but I don't necessarily know where they are. I can just find with the space key. So that's what I will recommend you to use if you go into 3D. Of course. But yeah, so that's about it for today. So next time we're gonna talk about game design, or specifically mechanics and emotions, and that's gonna be on March 17th, so next week. And then we're gonna have a small break because I'm going on holiday, and so I won't be here to stream. And so we're going back on the planning like the original one. So that means we have a bit of a gap between when I come, because the class after this one is gonna be on the 14th of April. So that's gonna be a bit before, but yeah, you'll have your time to start your prototypes and all of that. But yeah, so of course, so thank you for coming, and if you have any questions, well, please, I'm still here. Just send your questions, opinions. If there's something that's not clear or you want more detail on, don't be afraid. Yeah. No questions? Was that all crystal clear? That's okay too. Yeah. I hope it's not too early for the Americans, but it's so. I mean, I cannot change two classes at the same time. Time zones are always a bit weird. Yeah. Oh. Oh wait. Oh no. Okay. Okay. Well, cool. Well, if there is no questions, so, well, have a nice Sunday. Well, I'm glad to have you here. And well, see you next time. And if there's any questions that come up later, don't hesitate to ask them on Discord too. But yeah, see you around, fellas, and have a nice have a nice day. I guess. Yeah, afternoon otherwise. Bye.